My name is Yisol Choi. I'm a master's student at KAIST, advised by Professor Jinwoo. And today, I'll be presenting a paper, Item Vuitton, Improving Diffusion Models for Authentic Virtual Try-on in the Wild, which is accepted to ECCV 2024. And this paper addresses the virtual try-on task. So before we dive into the details, let me briefly explain what virtual try-on is. Basically, it's generating a human image wearing a specific garment. So it takes human image and garment image as inputs and generate the human image wearing the given garment as output. Actually, various methods have been proposed in the past to tackle this virtual try-on task, but these methods fail to generate natural-looking images or preserve the fine details of the garments. For example, this is definitely not the Mickey Mouse given in the input garment. So we propose a method for authentic virtual try-on by designing a diffusion-based model with comprehensive garment encoding. And this is an overview of our item Vuitton. Our main idea is to encode garment image with by separating it into high-level semantics and low-level features. So to do this, we use an IP adapter to encode the high-level semantics of garment and garment net to encode the low-level features of the garment. So our model consists of three main components: IP adapter, garment net, and try-on net for generating the actual try-on images. For high-level semantics, we utilize a pre-trained IP adapter to encode the high-level semantics like color or shape of the garment, and these semantics are conditioned to try-on net by a cross-attention mechanism. And for low-level features, we use a garment net to encode low-level features of the garment, and these features are injected into the try-on net via a self-attention mechanism. And as you can see, with low-level features from the garment net, we can preserve the fine details of the garment, such as graphical designs. And we also provide more detailed text caption of the garment with several attributes, because we basically utilize the text-to-image diffusion models as a backbone model. And as you can see, with the more detailed text caption, we can preserve the high-level semantics like neckline or sleeve types. But even with this detailed garment conditioning, our model often fails to preserve garment details in the wild dataset. So we propose an efficient method for test time adaptation and show that our adaptation method was effective. And these are the results by our virtual try model. And when you compare our model with previous methods, we observe that our method preserves high-level semantics like shape of the garment and low-level features like fine details of the garment. And also quantitatively, our model outperforms baselines in terms of garment detail preserving and image fidelity. And these are more try-on results by our model. And one of the images shown in here is of my advisor, which is very straightforward, I guess. And since our model really works well in the real-world scenarios, like user-uploaded photos, our method attracted a lot of attention from the public on social media platforms like Twitter, and we also had attracted attention from the AI developing communities like Hugging Face and GitHub by ranking the top one trending project. Yeah. And we also have a demo page on Hugging Face, so if you're interested, you can check it out and try it with your own photo. Yeah. Thank you.
Thank you. Good afternoon. My name is Jinwoo Kim, a PhD student at Yonsei University, supervised by Professor Sanjo Kim. It's my honor to be invited today, and I will introduce our recent work towards interpretable controllability in object-centric learning. So first of all, our research domain, object-centric learning, aims to understand what is an object and how they interact with each other in the latent space without any human annotated labels. One of the most famous baseline in object-centered learning is slot attention, and slot attention utilizes the concept of slot, which is a set of vector where each element is a latent vector that contain a object information. And slot attention adopts the auto-encoding structure, so we can train it in a self-supervised manner. And many recent works in this domain have tried to enhance the decomposing ability or object discoverability of slot attention. And one example is the slash, which is our previous research. So in this work, we have a question about, upon this enhanced object discovery model, what can we do with this well-captured object-centered representation? So the objective of this work is to control over object-centric representation, which is slot, to achieve a more usable and interpretable technique. So on our approach is based on the basic structure of slot attention. So on the slot attention's auto-encoding structure, we add a new branch which can update the slot so that the model can learn about how to update and manipulate the object representation. And here we use the image augmentation technique. So since we can easily get the augmentation instruction from the training process, we just adapt this information to the slot update process. And one good thing is that this framework is, in this framework, we can simply replace the augmentation parameter with the user's instruction at inference stage. And this is the detailed version of our framework's architecture. So the upper part is the original slot attention's autoencoding pipeline, and the below represent the newly added reconstruction pipeline using image augmentation. So here are the results. And given an input image, firstly, slot attention reconstruct the image, and during reconstruction, it also generates slot, which is object representation for individual object. And then user can directly control its object's properties by manipulating corresponding slots. So here we can change the position or change the scale or to change the color without any disruption on the other object or the background. And we'd like to emphasize that this accurate and precise control over individual objects can be achieved through the simple addition of an image augmentation pipeline. So here are more results on diverse data sets. And one more thing we wanted to say is that though the task we are solving may seem quite easy or trivial, however, it is not. We observed that even current popular foundation models such as Stable Diffusion and GPT-4 cannot handle this simple compositional or object-centric image editing task. And in addition to RGB space experiment, we also show that our framework can enhance the quality of object representation and by implementing a downstream task, property prediction. And lastly, the possible discussion points may include how can image level augmentation during training can be seamlessly translated into object level manipulation and inference? And how can we expand this approach to the in-the-wild images and more complex editing scenarios? This is the end of my presentation. Thank you for listening.
Hello, I'm Geo Ahn from Kyung Hee University, and I will present our work, The Bias, Learning Disentangled Action and Video Representations of Action and Scene. This is a joint work with my lemate Geonwoo, Young Kim from KAIST, and my advisor, Choi. Action and scene combinations in videos can be categorized into two types. First, scene action scene combination means that can be observed in the training data, such as dancing on the stage or dancing in the dance studio. On the other hand, unseen action scene combination means that cannot be observed in the training data, such as dancing on the crosswalk or running on the beach. And most datasets used for training lack of diversity in action scene combination. So model trained on this biased dataset naturally learns scene-biased representations. This scene-biased representation has a serious problem, which they fail with unseen scenarios. This scene-biased model focused on background instead of action, so predict the action of the following video like catching fish. And there is the scene-devised model. They may predict the action of the following video accurately like running, but they fail with predict the scene information, which is valuable for understanding a video. And it is not a desirable situation, right? In the case of human can robust regardless of seen or unseen scenarios. We can recognize the left video as running on the track and the right video as running on the beach. Why are humans the robust in the unseen scenarios? Because humans understand action and scene in a disentangled manner. We propose a novel framework, the bias, to learn disentangled action and scene representations. We use the disentangling encoder with slow attention. They learn complementary slots from the entangled backbone features, and we want to regularization to our slots, so we employ the action mask decoder and let the action slot to predict an action mask. Thanks to the complementary nature of the slow attention, we can guide action slot has the same effect as the guide scene slot. So when we use the DE and AMD during training, is the crucial for disentangling. Let's deep dive into the device. First, the backbone encoder feed the features to our disentangling encoder. And disentangling encoder use slow attention, which apply the attention over the slot axis, while traditional attention apply the softmax over the key axis. And through the slow attention layer, features gradually divided into the distinct feature. And we use the slot matching algorithm, which is the Hungarian matching algorithm, to select the action slot and scene slot. Given an action slot from DE, the action mask decoder predict an action mask. And to get a pseudo-ground truth for our slot, we use the training-free algorithm frame. This prediction task helps the action slot to contain only relevant action features. And now I will present our evaluation protocol used in this paper. We report the action and scene recognition performances in both scene and unseen scenarios. For unseen scenarios, we use SCUBA and HEAD dataset, which is a synthetic dataset created by mixing background from other videos. And we want to measure the balanced performances, so we use the harmonic mean as our main metric. First, we compare the performances using with and without disentangling encoder. So for the without disentangling encoder, we made a baseline using two CLS token, which called two token baseline. And when we use the disentangling encoder, we can gain the 7.5% in the harmonic mean. And when we use the action mask decoder, we can gain the 5.9% in the harmonic mean. And compared to the SOTA method, we achieved the highest harmonic mean compared to the baseline and scene devising method. And we evaluate also on downstream task using the data set with diverse characteristics. Device achieved the highest per harmonic mean, which means that the desentangled action and scene representation is the good pre-trained knowledge for various type of downstream data sets. In conclusion, we demonstrate we need disentangled action and scene representations for both scene and unseen scenarios, and our device effectively learn both representations. And our extensive experimenter demonstrate the robust performances of device. For future work, we plan to use the adaptively used for disentangled features for downstream tasks. Thank you for listening.
Hi guys, I'm Jeong. I'm affiliated on POSTECH and I'm very delighted to deliver this presentation in front of you guys. Well, I'm going to present about MVS adapter plug and play novel synthesis from a single image. This work was done jointly by POSTECH and RunAML and Cinnamon AI. I'm pretty sure that the guys here are already aware of the popular things that recent advancements in text to 3D or text to image or text to what or something like that. So starting from prompt to 3D, there were large developments of both data sets and text to image models. For example, like recently, the Observerse has been proposed so that there is currently available to use the large-scale 3D data sets. And also, after the appearance of Stable Diffusion, there has been lots of models like Stable Diffusion XL or any other variants. Well, thanks to the development of lots of text to 3D models and text to image models, there has been attempt to generate novel views from a single image without any information about other views. It means that when we have an object and we can only observe some parts of the objects, and we are attempting to generate the novel views in unobserved parts. But one of the main issues that appears in this task is that it has a multiple inconsistency. Let's first see about the example that I've pasted here. Well, 0123 is the state-of-the-art, the model before our model. When it attempts to generate 4 views together, and you can see that all the appearances are different. So because of this, we could find that when we attempt to build 3D on top of the generated images, we often struggle from multiple inconsistency. So here we want to propose a method that could handle this issue in an efficient way. So this is the overall figure of our model. Well, starting from the Stable Diffusion, we first freeze all the parameters of Stable Diffusion. The reason why we selected to freeze it will be introduced in behind part. And we additionally append 2 types of models. This is called adapter-based model because we froze the original parameters of Stable Diffusion. The first part is the view consistency cross-attention layer. Well, it consists of 2 main blocks, and the first one is a target views alignment, which allows generating multiple views together with an attention model. We adopt the perceiver architecture for this design, and we also introduce a reference view alignment that uses the cross-attention with the reference view that is used for an input. And second, we also introduce the global semantic conditioning. Well, we attempted to use the model that I've just introduced, but one of the problems I've observed is that without just a simple attention operation, the model fails to grasp the overall details of the reference view. So, it looks like quite convincing when we just observe the part of the object, but the overall semantics were not really reliably generated. So global semantic conditioning allows model to better grasp the overall semantic from the reference view by putting the clip embedding of the reference view. So these are the experimental results. Well, as you can see in the figure, our models successfully generate the images that has high multiple consistency, unlike the previous work. And also, one of the reasons I've just selected to use the frozen stable diffusion model is that we could show really high compatibility with control and LoRa. This was not really the first try to propose the way to using the control and LoRa, but the previous model has to retrain and requires extra fine tuning to use the control and LoRa because they fine-tune the stable diffusion model. So instead of that, we've frozen that, and so we can simply switch the network to the control net or LoRa so that we could guide the generation or sometimes stylize the generation. And also, we achieved the state-of-the-art MBS performance on both dataset, Google Scan Object and Observers. Google Scan Object is kind of out of distribution dataset. So these are the take-home message. We introduced a novel plug-and-play module for generating 3D from a single image, and also NVS adapter achieves state-of-the-art performance on various benchmarks in NVS. Also, due to its high compatibility, NVS adapter is combinable with control net LoRa without extra tuning. Thank you.
Good afternoon. I'm Junghyun Kim from Seoul National University. It's an honor to be here again at the Korea AI Summit 2024. I hope you're all enjoying the event, and I'd like to thank the organizers for giving me the opportunity to present our research. So today, I'm here to introduce our latest project, which we believe marks a valuable step forward in the field of embodied AI. Okay, so embodied AI is a rapidly evolving field with many fascinating topics. Among them, one of the most critical challenges is developing language-conditioned robotic policy, aka vision language action models. These models aim to empower robots to act on human instructions given the visual input. Several groundbreaking works have been developed in this domain, such as RT1, OpenX embodiment, and the current state-of-the-art model, OpenVLA. These models, built on transformer architectures, are trained on the OpenX embodiment dataset, which is the largest vision language action dataset to date. Impressively, these models can perform a wide range of tasks, performing 527 distinct skills, which is undoubtedly remarkable. But here's the critical question. Is mastering about 500 skills enough to call these agents a generalist? The reality is, there are countless additional skills that robots must learn to truly reach the level of a human-like generalist agent. For instance, imagine you've just purchased an assistant robot and wanted to perform a task, like opening your brand new trash can, a task it hasn't encountered during training. Then, how would you teach the robot? Currently, collecting robotic data is often based on experts who can operate robots or teleoperation systems. This approach can limit the ability of robots to expand their manipulation skills to handle the diverse tasks required in real-world environments. Our research addresses this limitation. The goal was to enable non-experts to intuitively teach robots new skills using natural language. So to achieve this, we developed a novel data collection method driven entirely by natural language. Here's how it works. First, the user provides an initial instruction, such as pour the dog food. The user then describes the required actions in natural language, for example, move left a lot. And finally, the robot executes these actions using a low-level action vector which is translated from the user's instructions by GPT. Next, we designed a vision language action model that can directly learn from action data expressed in natural language. For this, we adapted the architecture of CLIP, a well-known vision language foundation model. The key innovation lies in training the model to maximize the similarity between the action represented in language and the context consisting of visual input and the initial instruction. Here's the experiment results, and the results show that CLIP-RT outperformed the state-of-the-art model, OpenVLA, by 17% on novel tasks. This demonstrates the power of using natural language to expand the robot's capabilities. We've also prepared demonstration videos of CLIP-RT, but due to the time constraints, I'll just point you to our project page, where you can find all the videos and codes and further details. Thank you for your time and attention. If you have any questions, please contact me and I'll be happy to discuss. Thank you.
Good afternoon. My name is Inye, a doctoral student at Sungkyunkwan University, mentored by Professor Hyunjin Park. I will be presenting our research, radiomics film mammo, synthetic mammogram mass manipulation with radiomics features, which are published at MICAI this year. Our study began with one question: can you generate tumors with desired attributes? When you have an MRI sample with a tumor, what if we could remove that tumor and generate a new one with specific characteristics like tumor location, size, shape, and texture? While it's possible to control the tumor location and size using a mask, we wondered how we could manipulate more detailed characteristics like shape and texture. So we decided to use radiomics features. Radiomics features are often used to bridge high-dimensional medical images and clinical outputs. They are biologically meaningful markers and low-dimensional. We reversed this process and used them as conditions to generate synthetic tumors in medical images. The first result of this approach is radiomics film mammo, a method to generate realistic masses in mammograms, which are X-ray images of the breast. For our experiments, we used the public digital mammography dataset. Radiomics film mammo takes a masked image and tumor conditions as inputs and generates an inpainted image. To reflect the overlap of normal and abnormal tissues in two-dimensional mammograms, we used the other side breast image for normal tissue conditions and radiomics features with clinical variables for mass tissue conditions. We modified the stable diffusion in painting model as our backbone generator. Instead of using the text encoder in stable diffusion, we developed a custom tabular encoder for radiomics features. First, we verified radiomics will accurately generate tumors by checking the consistency of radiomics features. We compared radiomics features extracted from the synthetic tumors with the real features used as conditions. As shown in the violin plot on the left, the synthetic radiomics features looks very similar, closely match the real features, and you can also visually observe the synthetic masses generated using the same radiomics features as the real mass looks very similar. After confirming radiomics will generate tumors well, we explored its potential applications. For our experimental setup, we evaluated the radiomics field by comparing its performance with results generated using the different text-based conditions. This helped us understand its effectiveness in tumor generations. We applied radiomics field to improve performance in a downstream task, mass detection. This research showed that using radiomics features as conditions allow us to generate a wider range of messages, which improves the model's ability to learn from more diverse samples. Lastly, we visually confirmed condition-specific tumor variations. By fixing histogram and texture features and only adjusting shape features, we generated messages of various sizes from small to large. Due to the limited time for this presentation, I focus only on the key results. If you are interested, you can scan the QR code to access the full paper and source code. Thank you.
Hello. So my name is Soowon Kim, and I'm working with Dr. Sungwon Lee in the PRML lab in Korea University. And today I want to talk about phoneme level decoding of brain signal that are related to speech for open vocabulary BCI. So for the BCI that are related to speech, one of the key challenges that we face is that we don't have enough data set. So since if we wanted to train the model which can decode every single word and sentences in traditional way, we had to theoretically we have to train the model with every single word that we get from the participant of the EEG. So that's practically impossible. So what we wanted to propose is that if we can decode in phoneme level, which is in Korean 음소 단위, and then we can, that's the smallest speech sound unit, then we can reconstruct or decode unseen word or sentences if it's possible. So in our proposed framework, let's say we have a limited data set with a limited number of words, then we train the model so that it can decode all the phoneme sequences, and then theoretically, if it works well, then we can test it out the model with unseen word or sentences so that which consists of a phoneme that are in the training set, then hopefully it can reconstruct unseen word or sentences. So this is our data set. So obviously we only had 13 classes, which consists of 12 classes, word classes, and 1 resting state. So we had 22 participants and 100 trials per classes. So the data set, the amount of data set is really limited. And on the right side, we have example of transcription examples. So ARPA or IPA is actually the systems of how to show the speech sound units. So IPA is actually universal for any kind of languages, but ARPA system is more easy for computational purposes. So we were using ARPA. And as you can see here on the pie chart, even if we had 12 classes, we have a lot of phonemes inside of it. So actually we had, including start of the sequence and end of the sequence token, we had around 40 classes which we can classify as a phoneme. So here, this is, again, I'm gonna reinstate the framework. So during the training, we are gonna train the model with the phoneme sequences that are already seen in the training set. And then during the inference stage, we attempted to see the feasibility that the model can reconstruct the unseen word. And then the phoneme sequence is made, and then we used try search to find the correct word using CMU dictionary. So this is a little bit detailed about how we used the model, but since we have time limitation, I'm just gonna skip to the result. So here on the left is kind of boring because it is classifying very well on seen words because it's a spoken EEG brain signal, but interesting one is on the right. So this is confusion matrix where it attempted to classify the phoneme of the unseen word, but some of them, a lot of them are off the center, but
the red square represents the phoneme that are in the same group. So even though it was failed to classify correctly, but still manages to classify as a similar phoneme. So because of this, we were able to generate or have a word error rate of 63%, which is picking the one word out of 12 words. Then we had actually way above the chance level. And interestingly, on the right side, this is MDS plot. You can see when we extracted the feature and then do the MDS plot, you can see a lot of phonemes are grouped together, and those are in the same phoneme group. So yeah, that was really interesting insight we had. And that's all about we had today. And if you have any questions, just bug me. I'm just gonna stay around and eat dinner. Thank you.
I'm Iljung Kim, and I'm from the Department of Computer Science at Hanyang University. So today I will talk about flexible molecular alignment using diffusion generative models. So flexible molecular alignment is a process of aligning the 3D coordinates of a molecule to another similar molecule. So the coordinates of reference molecule and the graph representation of coding molecule are used to predict an aligned coding molecule structure. And flexible molecular alignment has applications known as cross-docking. And cross-docking is a method to predict the binding structure of a molecule by using the known structure of another molecule. So it's critical in drug discovery, and if we know the structure of reference molecule and proteins as here, we can detach the reference molecule. And if we have the graph of coding molecule, we can align the coding molecule as shown here, and then go back to the protein, we can predict the binding structure of coding molecule. So to solve this problem, we reframe the problem as generative task. So conventional method lacks flexibility and computationally expensive. So we reframe the problem as generative task. We can achieve high flexibility and computational efficiency. So to solve the generative task, we use diffusion model. So the starting coordinates of the coding molecules are sampled from normal distribution as green here, and it's generated as like demonstrated here. So by reframing the problem as generative problem, our model can handle more challenging problems, so where conventional method usually fails. And also by reframing the problem as generative task, our model can generate diverse outcomes as shown here. Green coding molecule can have two conformations, and our model can predict both conformations well. And to assess our model's performance, we use the decoy data set for self-alignment as a benchmark, and our model shows 44% better performance with 15 times faster speed than conventional method. So summary, flexible molecular alignment is critical in drug discovery, and by reframing the problem as generative task, our model can achieve high flexibility, high accuracy, and computationally efficient problem solving. Thank you for the listening.
Hello, my name is Geonwoo. I'm a master student at Soongsil University, advised by Professor Jinwoo. Today, I will present my paper titled Mule Multi-Grain Graph Learning for Multi-Behavior Recommendation. This work was supported by AI Innovation Hub's 12th research project at Jeonnam National University. In e-commerce, users exhibit multiple behaviors such as viewing items, adding to cart, and buy. Multi-behavior recommendation systems utilize diverse user behaviors to predict the items that the user is likely to buy. In this case, view and cart are auxiliary behaviors and buy is the target behavior. This approach is widely applied across various domains, including e-commerce and energy optimization. For better recommendation, our first motivation is to leverage the multifaceted relationship between different user behaviors. For example, as shown in the figure below, a user may have both view and buy to a laptop, indicating a certain interest. But user only view to a backpack, presenting a weaker or uncertain preference. These interactions should be treated differently as they carry distinct information. Our second motivation is that uncertain auxiliary behaviors often contain both noise and potential purchase, making it difficult to identify the user's actual preference. Therefore, it is essential to distinguish between these interactions. So we propose MULE that stands for multi-grain graph learning. Our first idea is multi-grain graph encoder that collects behavior information with diverse aspects. We sequentially aggregate behavior graphs from coarse to fine-grained while incorporating multifaceted relationship in the fine-grained behaviors. In fine-grained behaviors, we learn multifaceted relationship related to the target. Target intersective behavior graphs consist of auxiliary behavior interactions that occur with the target behavior, such as view and buy. With this graph, user certain interest information is encoded by light chain. On the other hand, target complemented behavior graphs consist of auxiliary interaction without target, such as only view. These graphs contain both potential interest and noise, but light chain is vulnerable to noisy graphs. So it is necessary to devise a denoising method to find potential interest. So our second idea is target-guided denoising attention to capture potential interest from uncertain auxiliary interactions. Our intuition is that the target embedding reflects the user's preference. If user's target embedding has a high similarity with items auxiliary embedding, the interaction is likely to be potential interest. By employing target-guided denoising attention, we assign more weight to interaction with greater attention, simultaneously reducing noise. Our third idea is multi-grain embedding aggregator that integrates the multi-grain graph embeddings using an attention mechanism. For enhancing prediction to the target, we adopt an attention mechanism considering the significance of each behavior. Our approach uses two-level aggregation, first focusing on coarse level and on fine-grained behaviors. The ranking score YN is calculated by the dot product of the final embedding. We optimize the ranking score using Bayesian personalized ranking loss with A2 regularization loss. We utilize 3 data sets sourced from real-world e-commerce platforms to evaluate our method. In recommendation performance, MULE provides better recommendation across all data sets. Specifically, in the TMO dataset, our method improved performance up to about 53% in NDCG. Evaluation studies show that all components in our method are effective. Specifically, in the first figure, incorporating the target-related behavior graphs leads to a significant performance improvement. This demonstrates the importance of considering multifaceted relationship. In conclusion, MULE learns multi-grain graphs through 3 effective modules to capture the user's true preference. Thank you for listening.
Hello, I'm Hyesong Choi, and I am a PhD candidate at Computer Vision Lab, Ewha Women's University, advised by Professor Dongbu Min. The paper I will be presenting today is titled Saliency-Based Adaptive Masking, Revisiting Token Dynamics for Enhanced Pre-Training, which was presented at ECCV 2024. So are you all familiar with masked image modeling? Mask image modeling (MIM) has proven to be a highly successful framework, driving much of the progress in self-supervised learning field. The process of this framework involves two main components: random masking of input tokens and calculating the reconstruction loss as the learning objective. And also, this paper is about pre-training and transfer learning, which are fundamental in self-supervised learning. Pre-training involves learning general features from large datasets, and then, in the transfer learning phase, we fine-tune the model on smaller and task-specific datasets. So, as I mentioned, the use of mask image modeling significantly advanced self-supervised learning in vision. However, its conventional approach relies on random masking. The drawback of random masking is that it treats all parts of image equally, regardless of their importance or relevance. This can lead to inefficient learning, as the model may spend resources or reconstructing less meaningful area of the image. Another key motivation of our work is the vulnerability of mask image modeling to masking ratios. So previous MIM method depend on carefully choosing masking ratio. Like for MAE, its ratio is set to 75%, but as shown in these graphs, even small changes in this ratio lead to noticeable drops in accuracy. So that is why we propose SBAM. First, A is the conventional random masking, which relies heavily on carefully tuned masking ratio, and B and C are our proposed method. B is saliency-based masking, which masks tokens with high salience. Using B, SBM makes our method robust to masking ratio changes, which allows us to introduce C, an adaptive masking ratio AMR. This AMR implements a tailored masking ratio for each sample. So using SBM and AMR together, we call it SBAM, our proposed method. For more details, SBM introduces token salience to prioritize and mask only significant tokens. SBM leverages a column-wise sum of the affinity matrix. So unlike conventional attention, SBM quantifies a token's overall contribution to the image using the column-wise sum in pixel space before the encoder. And this is the qualitative example of SBM. The important thing is that SBM demonstrates strong resilience across varying masking ratios. It is because SBM is less likely to mask out redundant or trivial areas, so it maintains stable performance compared to the baselines. SBM also enhances model performance and accelerates convergence. So we achieved stability across different masking ratios by SBM, and this allowed us to present an adaptive masking ratio, AMR. To put it simply, we count the number of tokens with saliency above a certain threshold and use that to set a dynamic masking ratio for each image. This way, each sample gets a ratio that fits the unique features. This figure shows an example of how AMR works. And this is the quantitative evaluation of SBAM, which represents the use of both SBM and AMR. Both results indicate a significant improvement in pre-training performance when AMR is applied with SBM together. The integration of SBAM into various baseline methodologies also demonstrate a notable enhancement in pre-training performance. So these are our contributions. We propose saliency-based adaptive masking, SBAM, a novel pre-training method that uses token salience for robust masking. And we also introduce an adaptive masking ratio, AMR, for tailored masking. Thanks for listening.